series have not looked, I mean, they look really practical and applied. You like thinking, I could use this tomorrow to change my tires, right? So far, not so much. The series just looked like, huh? Why do I care whether you add up these numbers and it converges? And even when you do add them up, you can't tell me what it converges to? I mean, most of my colleagues hate teaching calculus too, because they're like, how do you motivate that stuff? Okay, series have one use, really, one use that they're used for probably more than anything else, and that's to approximate functions. So let's start with one that we already know. Right? We already figured out a long time ago, we proved the summation, that if you have a number that's less than 1, and you raise it to the powers, 0, 1, 2, 3, you add it all together, you get something. I'm going to write that differently. I'm going to write it like this. Here's a function, g of x, which is 1 over 1 minus x. That's a perfectly good function, right? I could plug x's in and graph it and do anything I wanted with it. Well, but according to this, that's equal to the sum from n equals 0 to infinity of x to the n. Not quite. What do I have to write after that?
X is less than 1.
Only when the absolute value of x is less than 1, right? This doesn't equal this. This thing blows up if x is bigger than 1, because if you add 1 plus 1 plus 1 plus 1, you get infinity. Anything bigger than 1, you add infinitely many times, you get infinity. So this is equal to this only when... Well, that's pretty interesting, because that says this bizarre function, g of x, which is 1 over 1 minus x. Let's see, where's that undefined? At 1? And if I put large positive numbers, I get small negative numbers out. It must look like that. If I put 0 in, I get 1 over 1. Put a half in, I get... Okay. So there's what g of x looks like. Or g. So there's what g looks like. Well, this function, writing it like this, doesn't help us out here. But near 0, this is an accurate approximation of this. Because what do you get out if I put g of 0 into the sum from n equals 0 to infinity of 0 to the n?
0.
Let's see, I get 0 to the 0 plus 0 to the 1 plus 0 squared plus a dot. 0 to the 0 is 1. So sure enough, it at least agrees with it at 0. Okay, so what am I trying to convince you? I'm trying to convince you first that certain functions can be represented by infinite series. In truth, lots and lots and lots of functions can be written as infinite series, and so and you can get other ones from the ones we already have. Like suppose I have so I already know that 1 over 1 minus x is the sum n equals 0 to infinity of x to the n. So we already know that. Let's let x be negative t squared. So I'm just going to make a substitution. Put negative t squared to this. What do I get? I get 1 over 1 plus t squared. Put it in the other side. What do I get? I get negative t squared to the nth power. I don't like the way that's written, right? Because what can I do with it?
Negative 2n.
Yeah, negative t to the 2n, but careful, it's not negative t to the 2n close. I need to distribute the n to both, because that's a product, right? So negative 1 to the n, t to the 2n. Hey, an alternating series. So this function can also be written as a series. So f of x equal to 1 over 1 plus t squared is equal to an alternating series. And I thought those things were worthless. Again, this guy was only valid when x, absolute value of x was less than 1, so this one's only valid when the absolute value of t squared is less than 1. Oh, I wrote an x there, I should have written a t. Okay, so what's my point so far? Just to point out that we know at least 2 functions now that can be written as series. The truth is, every function can be, and when you use your calculator and you punch sine x, you know what the calculator does? It uses a series approximation of sine x. It doesn't know what sine is. It has no idea that sine is the y coordinate. It doesn't draw a unit circle and then try to find the y coordinate of the point on the unit circle. The sine function itself can be written as an infinite series. And so, if you want, your calculator's not going to add up infinitely many numbers, right? But if you wanted this pretty accurate, if you just added up the first 100, it'd probably be pretty accurate. In fact, there's a whole theory of mathematics that tells you how many of these you have to add up to be a certain accuracy. We won't worry about that. Okay, so 1, we can write certain things as series. 2, you already know how to start this process. So let me go back to bare bones basic calculus 1. I knew there was a reason we took that course. Did you get what you need? And then so let's look at a function. Whatever. Nice rational function. Looks like this. I only want to study it at one place, 1, 1. That's the only place I'm interested in. Now, if I asked you, write me an infinite series for this function right there, it might be a hard problem. If I asked you, can you come up, forget infinite series, can you come up with just a line that approximates this function right here? What would you do? What line would that be that's as close to the function as possible at that point? The tangent line, right? You did a million of those in Calculus 1. You never get out of Calculus 1 without computing the tangent line. Okay, so let me just tell you. I'm going to tell you what I'm going to do, then we're going to do it. We have that saying in industry. Tell them what you're going to tell them, tell it to them, then tell them what you told them. So I'm just going to call that T1 for my tangent line. Well, if you think about it, you never did this in Calculus 1, or at least I doubt you did it in Calculus 1. But if there's a tangent line that fits that curve pretty close, what are the 2 properties, calling this function's f and this is T1, what do T1 and f have in common? What can you tell me about it? They have this point in common, right? Mm-hmm. What does that say mathematically? How do you say that in function notation? They share the point 1, 1, right? So what does it mean that f goes through 1, 1? F of 1 is 1, right? How about t of 1? Is 1, right? So t of 1 equals f of 1, right? Now, how are we going to find this? What are you going to do? You're going to take the derivative of this function, right? And you're going to make that be the slope of this line. So they have something else in common. What's that? They have the same slope. So how do I say that mathematically? I say T1 prime at 1 is going to equal f prime at 1, correct? Now, how about T1 double prime? Is the second derivative of this one going to agree with the second derivative of that one? No. Why not? What's the second derivative of this one?
It's
Area.
Second derivative of a line?
itself? Or? Seems like a trick question.
Second derivative of any line?
Is
a point.
yeah, well,
Here's a generic line. What's the first derivative? M. What's the second derivative? 0. Because the second derivative tells you curvature, right? How much curvature does a line have? None. Okay, so the second, does this one curve at this point? Yeah. Does this one curve at this point?
No.
No, then their second derivative is not going to put Rachel. I'm putting her to sleep. 75% through the week. We're almost there.
This is it. No Friday.
Yeah.
Yeah, there is no Friday. Hang in there. You only got another 25% to go. Okay, so the second derivatives are not going to agree because this one's a line and this one isn't. On the other hand, what does have curvature that's a nice simple function?
X squared.
X squared, a parabola, right? But x squared doesn't go through that point, does it? However, the idea is good. Shouldn't there be some function that's a quadratic? We'll call that T2 of x. Now what do I want T2? I want T2 of 1 to be f of 1, right? I want it to agree at the point. I also want it to have slope the same as f prime. And I also want it to have second derivative.
Why doesn't x squared go through that point?
Because x squared looks like this. Oh, it does go through the point. Thank you for asking. I'm glad somebody's listening. X squared does go 1 to 1 squared to 1. Man. I'm sorry. X squared does go through the point, but do you see why the picture I drew is a better approximation?
Yes, sir.
It doesn't agree. It doesn't agree with it in terms of the derivative and in terms of the second derivative, right?
Yes.
So what I'm trying to create is a sequence of functions, and I'm not going to even say what the third one would be because I'm out of colors. We've got no
Where's the
green.
green ones.
We've got no green. The green's gone. Oh well. There's a cubic too. And the difference between that and the cubic would be what? I could get the cubic to agree in 3 derivatives, right? Because every time you add a variable on, mx plus b, ax squared plus bx plus c, each time you get one more variable, a, b, c. Next time, ax cubed plus bx squared plus cx plus d. Each time I get one more variable, that gives me one more degree of freedom, we engineers would call it. And that means that I can make one more derivative agree. Okay, so let's do the work now. Let's actually do the math here. The first part is calculus 1, right? So the first part is I want to find T1 of x is mx plus b. Fine. Okay, let's see. F of x is 1 over x. The derivative of that, that's x to the negative 1, is negative 1 over x squared, right? So f prime at 1 is negative 1. So my T1 of x is going to be negative x plus b. I want it to go through 1, 1. So I want 1 to be negative 1 plus b. So I want b to be 2. That's the best linear approximation there is to this function. You're not going to do any better. There is no line that fits this function better than that one. Because it agrees at the point and it agrees with the derivative, and you can't ask any more of a line. Right? Any other line, like that one or that one, well, they agree at the point, but they don't agree with the derivative, right? So that's the best I can do. Good on my algebra here? Am I making any mistakes? see, it's, that's my blue one. So now I can put my numbers on my graph. Perfect. Right? Goes through 0, 2, and 2, 0. Just like my graph showed. You abandon, you're adding the numbers after you plot it. Okay, good? Anybody out there? Good? Did I do my algebra right? Is that the function? Is that the tangent line?
Grasp all this.
All I'm telling you, all I'm doing is Calc 1 problem, right? Find the equation of the tangent line to this function at this point. So the way this would have been phrased in Calc 1 is find the equation of the tangent line to f of x equals 1 over x at the point 1 comma 1. Right? So you take the derivative of the function to find the slope. Derivative of the function is negative 1 over x squared. You plug the point in. That's my slope. So my equation, my line is y equals negative 1x plus b. Then I want to find the y-intercept, b, so I plug my point in, 1, 1. B is 2. There's my equation of my line. Everybody did that in Calculus 1. At least once. Yeah, Mark?
I understand everything you did, I'm just trying to figure out why you would need to find the tangent line of that function.
Don't need to. What I'm driving at, Mark, what I'm driving at is this. You tell me what degree polynomial you want. You give me any function. Here's the moral of the story. This is what I'm trying to drive at. You give me any function you want, call it out, and tell me the point that you want. A, f of a. As long as it's got infinitely many derivatives. The function's got to have infinitely many derivatives for me to do this. Then certainly, you knew from Calculus 1 how to find the tangent line, right? Call it T1. That's called the first degree Taylor polynomial. But we called it the tangent line in Calculus